new section, ordering the reals. So we have already seen that the system of real numbers forms a field. Now just like we put an ordered relation on the system of rational numbers, which allows us to say which rational number is less than which ones, we want to do the same thing for real numbers. So in this section we will do this. So let us start the section and see what some of the initial difficulties are and how to overcome them. So we start like this. We know that every rational number is either positive, negative, or zero. We want to say the same thing for the reals, that is for the real numbers. Every real number should be positive, negative, or zero. Now since a real number x is by definition a formal limit of some Cauchy sequence an, it is tempting to make the following definition. X is positive, that is x is defined to be positive if all of the terms in this Cauchy sequence are positive. Are positive rational numbers because they are rational numbers. And x is defined to be negative if all of the an are negative. And 0 if all of the an are 0. But this naive notion of positivity and negativity of a real number leads us to difficulties. However, let me put some ink first. One soon realizes some difficulties with this definition. To see what sort of difficulty one encounters if this naive definition is used of positivity and negativity of real numbers, we take these sequences. For instance, let an be the sequence defined like this: 10 to the power minus n for n greater than or equal to 1. That is, the sequence 0.1, if we write its terms in decimal expansion, the first few terms, then we get this. All of whose. Okay, so what are we writing? For instance, let this be the sequence, that is the sequence this, all of whose terms are positive. However, the sequence is equivalent to the zero sequence, and as such its formal limit is 0. So we can see that although the Cauchy sequence we have considered here is positive in the sense that all the terms are positive, but the formal limit is 0. So if we follow the naive definition above, then the formal limit should have been should be called positive. However, it turns out to be 0, and if we start calling 0 positive, then there will be some technical difficulties. Also, or we can just write one more sentence for this. So the formal limit of a Cauchy sequence all of whose terms are positive can become 0. Can be 0. Similarly, all the terms of the Cauchy sequence Bn are negative. So they are all negative rational numbers, but the formal limit is still 0. One can easily show that this sequence is also equivalent to the constant sequence, all of whose terms are the rational number 0. So the formal limit of this sequence is also going to be 0. So we can see that in this case also we cannot call the formal limit negative, okay, according to our using our ninth definition. So that means just like the situation of defining the reciprocal of a non-zero real number, we have to do some trick and we have to come up with some idea of a sequence bounded away from 0 positively and negatively. So that is the next definition that will salvage this matter. Or let us, before seeing the definition, let's take one more example. Another example is the sequence 0.1 minus 0.01 0.001 minus 0.0001 etc. This is also a Cauchy sequence which is a hybrid of positive and negative terms. Its formal limit is also 0, or you can write in words 0. So that's why we need a new notion to overcome these difficulties, and that notion is the next definition. So this is definition 541. It's reminiscent of the definition of sequences bounded away from 0. But now we are going to define two types of such things: sequences bounded away from 0 positively and sequences bounded away from 0 negatively. Let an be a sequence of rational numbers we say that an is positively bounded away from 0 if there exists a rational C that is positive such that an is greater than or equal to C for all indices n. So that means, in particular, if a sequence is positively bounded away from 0, then all of its terms are positive rational numbers. That is a consequence. The converse is not true. Okay. For example, all the terms in this sequence of rational numbers are positive, but one can show that this is not positively bounded away from 0. If the sequence is positively bounded away from 0, then all the terms are positive rational numbers, but the converse is not necessarily true. So in brackets we write in particular all the terms an are positive. The other half is also similar. We say that an is negatively bounded away from 0 if there exists a rational C greater than 0 such that an is less than or equal to minus C for all n greater than or equal to n. That means, in particular, each term an is negative. So this is the notion of sequences being positively bounded away from 0 and negatively bounded away from 0. Let us now illustrate this with an example. The sequence one point one, 1.01, 1.001, 1.0001, etc. is positively bounded away from 0, and the reason is this: all the terms of the sequence are greater than or equal to the positive rational number one. So that's why it's positively bounded away from 0. That is, you can see that if you think of these numbers on the numbered line, then 1.1 is the farthest one from 0. When we take 1.01, we get a little closer to 0, and then we take 1.001, we get a little more closer, and then we keep getting closer to 0. But the thing is that all these terms, 1.1, then here you have 1.01, 1.001, and so on, all these terms are greater than or equal to 1, which prevents them from getting any closer to 0 and definitely prevents them from slowly approaching 0. So this one stops everything. So that's why this sequence is positively bounded away from 0. Like that, you can consider a sequence that is negatively bounded away from 0 by considering the negatives of these numbers. The sequence okay, what the hell did I draw there? What I draw is wrong. 1.1 will be here, 1.01 will be here, 1.001, and so on, because they decrease towards the negative x-axis, and here you have 1 somewhere, and here you have 0. So all these terms of the sequence are greater than or equal to 1, so they are positively bounded away from 0. I drew the exact opposite thing. Sorry for that. Now the sequence minus 1.1, minus 1.01, minus 1.001, minus 0 0 0 1 and so on is negatively bounded away from 0. In this case, the previous diagram would work, because here the number that is farthest away from 0, all of them lie to the left of 0 because all of them are negative. The farthest one is minus 1.1. Then it goes like this. Here you should not think that these are equally spaced. You can understand, but then all of them are less than or equal to minus 1. So they are negatively bounded away from 0. But at the same time, you can consider a sequence which has positive as well as negative terms. The sequence where the terms alternate between 1 and minus 1 is bounded away from 0. Recall what bounded away from 0 means. It means that there is a positive rational number C such that the absolute values of all the terms of the sequence are greater than or equal to C. In this case, for this particular sequence, that C can be taken as 1 itself, or maybe some smaller positive rational number. Whatever you take C to be, the fact is that this sequence is bounded away from 0. But it is neither positively bounded away from 0 nor negatively bounded away from 0. Because positive boundedness from 0 implies that all the terms should be positive. Like that, negative boundedness from 0 implies, it demands that all the terms be negative. Here, however, that none of them is possible, so it's neither positively bounded away from 0 nor negatively bounded away from 0, although it's bounded away from 0. So we can see that we can have this property of being bounded away from 0 in without satisfying any of the other two things we have defined in this video. The converse, however, is true. If a sequence is either positively bounded away from 0 or negatively bounded away from 0, then it's a consequence, easy consequence, that the sequence must be bounded away from 0. It's clear that if a sequence of rational C's positively bounded away from 0 or negatively bounded away from 0 then it is bounded away from 0. And one more thing that should be noted is that a sequence cannot be simultaneously positively bounded away from 0 and negatively bounded away from 0, because same reason, positive boundedness means all the terms are positive and negative boundedness means all the terms are negative. So they cannot happen simultaneously at the same time. Also, a sequence of rationals cannot be both positively bounded away from 0 and negatively bounded away from 0. Okay, so these are some examples and easy consequences of this idea of positive boundedness and negative boundedness of a sequence of rational numbers. Now we state the state means now we define what we mean by a positive real and a negative real number, and the definition will naturally be based on this idea. So this is definition 3. A real number x is said to be positive if there exists a Cauchy sequence, actually, that I should write. A Cauchy sequence an of rational numbers that is positively bounded away from 0 such that x is the formal limit of such a sequence. Okay, x is said to be negatively bounded away. Oh, sorry, I got carried away. Is said to be negative if there exists a Cauchy sequence Bn of rational numbers, that is negatively bounded away from 0 such that x is its formal limit. Okay, so this is our definition of positivity and negativity of a real number. Now this definition raises a lot of questions. For example, if we are given a real number that is not equal to 0, will it really be either positive or negative? And for that matter, if you have a positive real number, will its negation be negative? That is, these are the things we expect from our definition, and they will turn out to be true. So in that direction, we have this proposition which basically answers our queries about this definition, that whether this definition will create a notion of positivity and negativity that will match with what we expect from real numbers. So it has a name also, basic properties of positive reals. And the statement goes like this: let x be a real number, then exactly one of the following three you can probably guess what I am going to write. I am going to write the conditions for trichotomy. Three statements is true, and statement A is this: x is 0. That is one statement. Statement B will be x is positive, and statement C will be x is negative. One of them must always be true, and only one must be true. X is 0. Then statement B is, they are using semicolon in between. X is positive and C, X is negative. So this is one part of the statement of this proposition. More is also there. A real number x is negative if and only if the negation of x minus x is positive. These are properties we have always used when working with real numbers. And one more thing is this: if x and y are positive real numbers, then so are their sum and product. And the proof of this proposition is the first exercise at the end of this section. So for proof we write see exercise 541. Okay, now we know what a positive real means. So let us now see that this notion of positivity of real numbers is whether it's actually consistent with the notion of positivity of rational numbers, because we have embedded the system of rational numbers inside the system of real numbers. So it better be the case that the two notions match, because otherwise we have a problem. Note that if Q is a positive rational number, then the Cauchy sequence, all of whose terms are equal to Q, is positively bounded away from 0. Positively bounded away from 0 because each term is greater than or equal to Q, and Q itself is a positive rational. So this is positively bounded away from 0. As such, according to our definition, its formal limit, which again is Q because of how we embedded the rationals into the reals, is a positive real number. So our notion of positivity in the system of real numbers is consistent with that means with the notion of positivity in the system of rational numbers. So that means our definition is okay. So the embedding of the rationals into the reals is not just nice in the sense of the algebras of this system. systems, that is not only are the addition and multiplication in the systems nicely what can I say, they behave nicely with one another, in the sense that if you think of a rational number as either a rational number or a real number, and then you say you have two rational numbers and you think of them as rational numbers, then you have a definition for their sum. And at the same time, thinking of them as two real numbers, for that also you have a definition of sum. So they basically give the same thing, where sameness is measured with that embedding. Okay, and the same thing is true here also. Positivity is preserved by the embedding. Similarly, the notion of negativity in the system of real numbers is consistent with that. That means the notion of negativity in the system of rational numbers. Okay, so now we have a definition of positivity and negativity in the real number system that behaves like how we expect them to behave, and that is guaranteed by this proposition. Now, once we have positivity and negativity in the system of real numbers, we can define absolute value and order. That is, we can now say which real numbers are greater than which real numbers and things like that. So that's where we are heading now. So this is the next definition. This is definition 5. Absolute value. Let x be a real number. The absolute value of x, that means this is the notation for the absolute value of x, same notation that we had when x was a rational number, is defined to equal x itself if x is positive, minus x if x is negative, and 0 if x is 0. While making this definition, we may be tempted to write x greater than 0 in place of this phrase x is positive. But the problem is that greater than, less than, those things have not been defined yet. Now only they are going to be defined. So we cannot use them prematurely, although we are very familiar with these things. See, that is the problem. We already know of these things. We know that they are true, but we haven't quite seen why they are true. Now only we are encountering the reasons for their truth. So the difficulty here is that we have to suspend our prior knowledge and view these things in a way as if we are viewing it for the first time, and that in itself is a challenge, because if we become too careless, then we inadvertently may end up using something without first defining it. So at every step we have to be extremely careful. Okay, now we have absolute value, and finally we are now going to define order on the system of real numbers. So this is definition 6. Ordering of the real numbers. And the definition is quite easy. Let x and y be two real numbers we say that x is greater than y and write this notation if x minus y is a positive real. Okay. We say that x is less than y if x minus y is a negative real number. Okay, using properties of that proposition where we stated that a real number is negative if and only if its negation is positive, using that one can show that x is greater than y if and only if y is less than x. Okay, it's rather easy to show that. We write x greater than or equal to y if x is greater than y or x is equal to y. Also, we write x less. Is it really necessary to write this part? I can't figure that out. That is, I can't figure out at this moment whether this will follow from this. You can see if it follows from this, then fine, otherwise you just assume it. Okay, this is just about a notation. Also, we write this if x is less than y or x is equal to y. Okay, so that is the definition of order. pretty straightforward, and we are familiar with this definition also. So let us now again make a comparison with the similar definition we had in the system of rational numbers. So the author writes, comparing this with the definition of order from this definition of order in the rational number system, from definition 4 to 8, we see that order on the reals is consistent with order on the rationals, and we also have to explain what that really means. Consistent This means that if P and Q are two rational numbers, then P is less than Q as rationals. Will it be clear if I just simply write P is less than Q as rationals? It means that we are treating P and Q as rational numbers and P is less than Q according to the definition of order we have in the system of rationals. If and only if P is less than Q as reals. That means whether you consider P and Q as rationals or reals, if P is less than Q in one system, then it's also the case in the other system, and conversely. And similarly for greater than. Greater than is just another way, truly speaking, another way of writing less than. And finally, in the same way, we see that the definition of absolute value for the rational numbers is consistent with the definition of the absolute value for real numbers. For real numbers, these things are quite straightforward to verify. Okay, now before we make the next proposition, let me feed this some ink. Now that we have defined order, absolute value, those things, so the next natural thing to do is to see that all the claims in proposition 429 which explores properties of absolute value and order in the system of rational numbers in this system, that is see whether they are also true in the system of real numbers. Let me write the proposition there. So this is 7. All the claims in proposition 4 to 9 which help for the rational numbers continue to hold for the real numbers. In this proof, we will not actually prove all the claims that we have there, I mean their version for the real numbers, but we will prove only one, leaving the rest of them to the second exercise. So the proof starts like this. We just prove one of the claims leaving the rest to exercise 542. Okay, so the one we are going to prove here is that if x, y and z are three real numbers such that x is less than y and z is a positive real number, then xz is less than yz. That means positive multiplication preserves order. It's that thing. So let x, y and z be real numbers such that x is less than y and z is positive. Okay, now since x is less than y, by definition y minus x is a positive real number. Y minus x. Okay, let me just go to the definition of positivity actually and see whether we really have y minus x, positivity of y minus x to be the criterion. So this is just definition of positivity and positively bounded. So where is that one? Here. X is greater than y if x minus y is a positive real. Yes, that means if y is greater than x, that means y minus x is a positive real number, and this is by definition. So by the proposition that we mentioned but we did not prove, which we named basic properties of positive reals, that proposition tells us that the product of this positive real number and z is again a positive real number. So by proposition (544), this is a positive real number. Y minus x times z is a positive real number. Now, using algebra of real numbers that we have seen in the previous section, this becomes yz minus xz. So yz minus xz is a positive real number. So again, by definition of order, yz will be greater than xz, or in other words, xz will be less than yz. But then xz is less than yz. So this completes the proof of the fact that multiplication by a positive real number does not reverse the inequality. It changes the numbers in the inequality, of course, unless z is 1, but it does not change the direction of the inequality. So this is the incomplete proof of proposition 547. We have to complete it in the second exercise. So I end the video here itself. There are many more things in this section, and we will slowly have a look at them, and we will see how actually this order that we have defined here in this video matches with what we have been working with all along. That is what we normally know as order when we write, say, 2 less than 5, or for example 1 over 5 is less than 1 over 2. It is this order precisely as far as the basic properties and everything else is concerned. So that will be all for tonight in this video. If you have any doubts regarding this and anything else regarding the subject, you can always comment in the comment section below. So that's it. This is me, Lucifer, from a mathematical room. Have a nice night.